Okay, so hi everyone. I'm Adrien Piquerez from the Scala Center, and I'm going to talk to you about the debugger for Scala 3. And why debugger? Because debuggers are cool, and also because they are very useful. Before starting, maybe I will propose you like a little game, okay, about Scala runtime. So we have a simple expression, foo.bar, and the question is, what will happen at runtime? Okay, so if we assume that this expression is a Java expression, it will be straightforward to answer. Like we can say that foo is a value, and then there is a method in foo which is called bar, and we just have to evaluate bar. So only one thing will happen. But for Scala, things are a bit different. Let's try to make a few hypotheses. Can we say that foo is a value? So maybe, yes, foo could be a value, but it can also be like a method. In such case, we need to evaluate it. Or it can be a lazy value that we need to initialize. Or it could even be a biname parameter that we also need to invoke. Okay, so maybe foo is not a value, but at least foo should be evaluated first. Well, in some case it won't, because foo could take, so if it's a method or a function, it could take context parameters. And in such case, we need to evaluate the context parameters first. Okay, after foo, what will happen? Will bar be evaluated just after foo? No, it's not that simple, because maybe foo needs to be converted into something else before we can select bar out of it. And also because bar is a method, so it can take context parameters that could be evaluated, or it can also take default parameters that we also need to evaluate. So as you can see, for a simple expression like this one, in Scala, there are many different possible execution paths. So it's kind of hard to understand sometimes what happened during the runtime of Scala, and especially for beginners. And that's why maybe debugger can be useful and can help us understand how a Scala program will will be executed. Okay, so my main messages during this talk will be those one. So first, a Scala debugger is not the same thing as a Java debugger. So Scala runs on the JVM, but if we use a Java debugger, we will get a lot too much information, and that won't help us much on debugging Scala. Second thing is we are building a Scala debugger here at the Scala Center, and it's available in Metals. So you can already try it. It's going to get improved, and hopefully in a few months, we'll get a really good Scala debugger. Last thing is that we need you. You should support us. So please use this debugger and report bugs and quirks. As a bonus, from this presentation, you will, I hope you will discover some cool debugging features. So in modern debuggers, there are many features, some that are well known, like breakpoints, and some that are less known, like data breakpoints maybe. So you will learn a few of them. And you will get a sense of how things work internally. Yes, this talk will get very technical, so I hope you like technical things. We'll see what happens in the debugger itself, but also in the Scala compiler and in the Java bytecode. Okay, so the project that we started 2 years ago is called the scala-debug-adapter. And the scala-debug-adapter takes its roots in many other different projects, like Bloop, Metals, or the .tid. So the idea was to simplify things by grouping together all the debugging implementations that we had in Bloop, in Metals, and in the .tid. So now all is in the same project, the scala-debug-adapter, and the other projects like Bloop, they depend directly on the scala-debug-adapter. So we could remove some code from Bloop and use directly the debug adapter as a library. For the .IDE, so the .IDE is not used anymore. It was the language server for .I back in the days. And there were some good features for debugging, like expression evaluation, and those we took out of it to put them in the debug adapter so that everyone can use them in metals. So a lot of credits of what I will show you today goes to the people that contributed to those 4 projects: Bloop, Metal, the .IDE, and the scala-debug-adapter. So why do we call it the scala-debug-adapter? On the right, we have the program that we want to debug, and it runs on the JVM. We call this program the debuggy because that's the thing we want to debug. On the left, we have the user interface, and it will be, in our case, VS Code, but it could be any other code editor. So in this user interface, we have things like Scala files, breakpoints. We can see the variables, the call stack, and we have a debug console. So how can the interface interact with the debuggy? So in the JVM, there is an interface for debugging, which is called JDI, so Java Debug Interface. But VS Code is a language agnostic tool, so it doesn't know anything about Java or the JVM. To talk with the debugger, it uses a protocol called DAP for Debug Adapter Protocol, and this is the same protocol that is used for any language when debugging in VS Code. So to translate JDI into DAP, we need an adapter, and that's what the Scala debug adapter is. So it's something that can translate JDI into DAP so that people can use a debugging interface in VS Code. So if you want to learn more about DAP, you can go to the DAP Debug Adapter Protocol website. You have some explanation of why we need an adapter. So instead of having one debugger for each language in each editor, we only have one debugger for each language, and that simplifies the work. It's a protocol, so it's defined as a series of requests and responses. You can see the entire specification here. There are a lot of different requests, some that we can use with the Scala debugger and some that we cannot. So I don't know, maybe like step back is something that we cannot do with the Scala debugger, but that is possible in other languages. So if you want to learn about modern debuggers, I think this is a really good reference. So maybe if we go to source breakpoint, so a breakpoint in a source file, we can see that the breakpoint is defined as a line number, but also maybe as a column number, and we can have condition or messages to log, those kind of things. The debug adapter protocol is implemented for many languages, and in particular, it's already implemented for Java. So it's the Java debug. So Java debugger, it's based on the Java debug server, which is implementation DAP for Java. It's a bridge between VS Code and the JVM, and it uses the JDI. So it looks like that's something we could use, like a bridge between VS Code and JVM using JDI. Okay, so let's try to learn about the architecture of the Java debug server. Most of the implementation is in a single module called debug core, and that module has a single dependency, which is JDI. So that's something we can reuse. The rest of the implementation of the Java debug server is in a module called the plugin. And the goal of this module is to bridge between the build tool, so the Java build tool, so in that case it would be Maven or Gradle, to bridge between that and the debugging itself. And they implemented it using the Eclipse libraries. So in the case of Scala, we have different build tools. Our build configuration are different, so we cannot reuse org Eclipse directly. So what we will do, okay, sorry. The interface between the plugin and the core is not so big. It's only 4 different interfaces that we need to implement. So in our case, we will replace the debug plugin with a scala-debug-adapter. We will use different libraries. We'll see which one. And we only have basically to implement those 4 interfaces. Okay, so this is our to-do list. On the left are the features that we can get from the Java debug server. Some we get for free, or almost for free, like the launch request. So to get the launch request, we need just to configure the Java command line. And for the attach request, we just need to find an available port and connect to it. Some we get we get for free, but they are not really usable yet. For instance, pause, continue, or step in, out, over. That's something we can do with JDI directly. The problem is we won't be able to know in which file, in which Scala file we stopped. So to solve that, we need to implement those interfaces. And the first one is ISourceLookUpProvider. So the goal of the ISourceLookUpProvider is to map the source file and lines, so the Scala source file in our case, and Scala lines to Java class files. Here is the definition of the interface. We have a first method, which is get source file URI, that takes a class name, so a fully qualified class name from the JVM, and which returns, which should return the source file that generated this class name. And to the opposite direction, we have this method that takes the URI of a source file, some lines in the source file, and that should return an array of class files. Okay, that's because in a single Scala file can generate many different class files. So that's why it's an array here. Okay, let's look at the first method and how we can implement it. So we'll take an example. What if we want the source file of this class file? What we can do is to decompile the class file using something like JavaP. So JavaP is a decompiler of Java class files. And in the decompiled result, we can see there is the name of the source file. And then in the source jars and source directories, we can try to find this source file. So chances are there are only one, but in some cases we can find many source files with this same name. So here we need some heuristic to find the good one. And the heuristic can be, okay, let's look at the package, or it could be, let's try to parse the source file to see that indeed there is this class defined in it. By reading all the class files, we can build this map from class name to source file. On the other direction, so now we have the path of a source file and an array of lines, and we want to know where, what are the class files associated with those lines and source file. So again, we can find all the class file of the source file and then decompile them to see the line number table in the class files. So the line number table is something added by the compiler into the class file to map from the lines to the bytecodes. So here we can see that line 28, which we want here, in the source file is associated with the bytecode 0 of this method, get all nodes and unfun. So again, if we read all the class files, we can build a map from source line to class file, and that's how we can implement the source lookup provider. So that was it for the source lookup provider. Now we can pause in the program. We can see the call stack, the variables, and we can know exactly where those things are defined in our source files. So that is kind of the state of the debugger in Metal that we had like 2 or maybe more, three or a bit more years ago. Okay, the next thing to implement is the evaluation provider. So the goal of the evaluation provider is to evaluate expression at runtime. And for Scala, it was implemented in the .t IDE, and we took this implementation and we adapted it for Scala 2, and we also improved it for Scala 3. And that's how and now we'll see how. Okay, as interface of the evaluation provider, there is a method that takes an expression, a thread, which is the thread in which we want to evaluate this expression. And from the thread, we can get like the stack trace and the top frame of the stack trace, or like the frame at this depth in the stack trace. And then from the frame, we can get the name of the method, the source file, and also all the variables, the local variables. Okay, so let's say the program paused in this method, get all nodes, and that we want to evaluate this expression. So read some nodes out of those bytes. Okay, how can we, what do we need to do to evaluate this expression? First, maybe we need to parse the expression and then check that the expression is correct in terms of semantic. So that means we need to type check it. But this is not enough in Scala. We can also have like context parameters. So maybe we also need to resolve them. Or maybe this method read is overloaded, so we need to find the right overload. So to do all of that, we already have some tool, and that tool is the compiler itself, so the Scala 3 compiler. And this is basically how the compiler works. It's a simplification. So compilers are made of phases. So the first phase is a parser. It takes the source files and it transforms them into trees, abstract syntax trees. Then we need to know if this tree is correct. So we type the tree, and we get a type tree. Then in Scala 3 there is a series of phases called the Piquerez phases that are responsible to do macro expansion or inlining methods. So after Piquerez phases, we have a fully expanded trees of Scala code, and then we need to make something that can be executed. So we will need to simplify those trees through the transform phase to something that looks like JVM class files, and the backend will then emit those JVM class files. So that's basically how it works. Okay, so to evaluate the expression, we need to put the expression in its context. And here the context is some lambda in a method. So what we do is that we insert a valdef node in the tree, whose name is expression, and whose right-hand side is the expression that we want to evaluate. So this is the first phase we had to create this new expression compiler that can compile expressions. Then the typer does its job, and it does it well. So now we have a fully typed expression. We see that the type of the expression is a note. We see that read is a method that can be found in a static object called default in the package upickle. And we'll see also that we need these context parameters. Okay, so this is almost something that we could evaluate now. But to evaluate something in the JVM, we need to inject it somehow, and the JVM, and to do that, like the JVM can load new classes, for instance. So maybe we should create a new class and create a new method in this class, evaluate, and put the fully typed expression in this new method. So that's what will the extract expression phase do. So this is almost it, but there is a problem, and the problem is that bytes is a local variable and it's not accessible anymore. But debugger here can access bytes from the thread, so it can inject it and all other local variables into the evaluate method. So now the evaluate method takes a map of local values. The string here is the name of the local values, and that's the value. And we can now resolve bytes like this. So the extract expression phase will generate all of this, and then we'll be able to evaluate, so to load the class expression, and then to evaluate its value and return it to the debugger. Another example is this one. Now we want to evaluate just directory, which is a field in the current class here. And here we have another kind of problems, which is that directory cannot be accessed from another class. So here, expression. So to solve this, we use some helper method that use Java reflection. So for instance, here we want to access a field. So we call this method getField in object this, whose class is file repository, and we want to access the field name directory. And this helper method is implemented using Java reflection. Okay, so that's the extract expression. Okay, this works pretty well in most of the cases, but we have some really high-level features in Scala, and some Scala-like concepts cannot be directly translated into Java. We need to transform them first. So in some cases, the extract expression doesn't know all the information that we will need to evaluate the expression. So I have an example for that, which is lambda lifting. So in Scala, we have a concept of local methods. So here I have a method m, which is inside another method main. It's a local method, but that thing doesn't exist in Java. So the transform phases will lift this method out of the method main and put it into the class itself, like this. So here I suppose I want to evaluate x on this line, but on the runtime I'm not. I will be in this other method which is lifted, and whose name is now $1, and which take an argument x1, which is x. So x was a local value, so it cannot be accessed from the lifted method. So that's why we need to pass it as an argument. Okay. So now the thing x that I want to evaluate is x1. And the problem here is that extract expression doesn't know about the new name x1, because the new name will be created later in the phases by the lambda leaf phase, which is a transform phase. Okay, so in the extract expression, it's too early. It's too early to know exactly how we will be able to evaluate by reflection the term x, which is captured by method m. So we call this magic method that does nothing, and we attach to the method this information. So we say like this reflect eval need to evaluate the term x that is captured by the method m. And then later, after the transform phases, we will be able to know that m has been lifted and that there is a captured argument whose name is x1, and that's the one that we want to evaluate. So this is where we put the resolve, reflect, eval phase after all the transform phases and just before the backend. What time is it? I don't have much time, so maybe I will go faster on this one. This is another example. Yes. So this is another example of what resolve, reflect, eval can do. And in this case, we want to call m, but m will have a different name, and it will take a captured argument. And again, during the extract expression, we don't know what the name of m will be, and we don't know how many arguments it will capture. So we delay this to the resolve, reflect, eval phases like this. And that's how it's done in the end. Okay, so we saw that the resolve, reflect, eval can encode Scala names to Java names. It can resolve captured argument. So an argument can be captured by a method, as we saw, but it can also be captured by a class if it's a local class, or if you put a class inside a method. But it can also do many other things, like invoking by name arguments and lazy values, or boxing and unboxing value classes, or dereferencing captured vars. So when a var is captured by a method, and because we might want to assign something to it, the compiler will box it into a ref object, and we need to dereference it during evaluation. And also we take care of assigning new values to captured files. Okay, that's it for resolve, reflect, eval. Something I forgot to say is that extract expression goes just after picker and not typer. And that's because we want maybe to be able to evaluate like macro methods or inline methods. So by putting it just after macro expansions or inlining, we get that for free. Okay, this is it for evaluation provider. So now we also have conditional breakpoints, which is a breakpoint that can stop if a condition is true. And we also have expression evaluation in the debug console. Really cool. And that's kind of the state of debugger in the current version of methods. Oh no, because also we have completion providers. But for this one, I will use Joker because the completion providers do autocomplete in the debug console. But autocomplete is something that metals do very, very well. That's very, very well. So we don't need the debugger to do it. So it's implemented in metals directly. So metals intercept those requests and answer to them. For the last one, the code replace provider. So the idea here is that we can change the source file, that the source file can be compiled, and that then we can load the new class generated by this. This is not yet implemented. So this is my second Joker. But maybe that's a cool thing to contribute to. So if someone wants to try that, that would be very, very useful. Okay, time for a demo. So for the demo, I'm using the application that I created as an example for last year's Scala-Com. So it's a simple web application. There is a web server here with a few endpoints, and endpoints to get many nodes. So it's a Notepad application, so we can get many nodes, we can create a new node, or we can delete one. And I put a few breakpoints in this application. Okay, so let's see if I can start the debugger. That's it. So the debugger started. So now I can reload my web page. And to reload, it will need to get all nodes. So that's why it stopped here. Okay, so let's see what's in get all nodes. Here we are in file repository. It reads many files, and then it tries to parse them using upickle. Okay, what's the first file? Maybe this one. Can I try to evaluate something like bytes? Okay, bytes is an array of bytes. And maybe I can cut them like this. Okay, it worked. And this is the note that we passed. So content is Scala-Com is awesome, and we have a title, Welcome to Scala-Com. A new file, let's go. Okay, so the page reloaded successfully. So this expression compiler, I think it is very, very robust. And it can do really crazy things because Scala is a crazy language. You can do many, many things with it. So maybe let's take another example. We can maybe try to delete this node. Okay, what can I do? One thing I can do is that I can create new method, for instance. So method, but now it will return just file, maybe, yes. And then I can call m. It worked. Another thing that it can do, it can call macro method. So I have a macro method somewhere defined in macros here in my project. And it's a simple macro that just shows a type of some expression. So maybe I want to know what the type of file. Okay, so in this case, it's simple. It's a Java, a simple Java type. What about, I don't know, seek of 1 and 3? Seek of Scala int. Okay. So this is debug console. It's not a REPL. So I defined m earlier, but I cannot use it anymore. It would say I don't know what m is. We have good error reporting from the compiler itself. What else can I show? Or maybe I can show that I can restart a frame. Okay, maybe I do it again. So okay, I'm here. The file is going to be deleted, but instead I want maybe to resolve the path again. So I can restart the frame, and it goes at the beginning of the frame. So it doesn't go back in time. So it will not undo the things that are already executed, but it can just jump out of the method and in the method again. That's what happened. Okay, oh, breakpoints. I can show a few things about breakpoints. Okay, maybe not here. Let's try on the web server, get all nodes. I can add, so a condition, but maybe here I want to have a hit count. So I want to stop only the first time the program goes through this method. Okay, let's try. Okay, let's delete this one. Okay, good. So now I can reload my app 4 times, and it should stop the first time. So 1. Okay, it didn't work. Demo effects. I don't know. Disable breakpoint. Add the breakpoint. Edit it. Hit count 2. Good. It doesn't work at all. Sorry for that. Maybe if I restart the application. Okay. Now 1, it didn't stop. 2, it stopped. Okay, so that works this way. What else? Maybe I want to, so this is create node. Okay, maybe I want to stop here if title.size is bigger than 3. So now, okay, let's continue the program. Now if I create a new node with a short title, like, I don't know, okay, shouldn't stop here, but okay, it didn't stop at my conditional breakpoint that was here. But now if I create one with let's debug, okay, it stopped because the expression is true now. Okay, so that's about it for the current state of the debugger. Okay, so next slide. Is it good enough? Like, can we have a more Scala-friendly debugger? And I think we can. And I want to show here why. So one thing is, I need to go back in time to show it, to show that to you. So I use another version of the debugger, reload the project. Then I'll start my application again. Okay. And I create a new node, this one. Okay, it stopped here. Here, basically, we have a Java debugger with some Scala expression evaluation. But in many cases, the Java debugger will show too low level of implementation of the Scala runtime. So one example is this one. What if I step into create method? So create method is a method in a trait, and this trait is implemented by this class file repository. So what if I step into it? It doesn't go directly to the implementation of the method. Instead, it goes into some weird place, so that we can see on the stack here. It's a method whose name is create node, but it's not a method in the trait, it's a method in the class. This method doesn't exist in the class. It's generated by the compiler. And we call it a mixing forwarder. But really, it's a detail of how Scala is implemented. It won't help me to debug my program. What if then I step into that method again? I go in another weird method, which now is create node with a $. It's a static method in the trait itself, so in the corresponding Java interface. And I don't go to the implementation directly. So this is another annoying step that I really don't need. Same if I step into again. Now I am in the implementation. Okay, so maybe one thing we can add to the debugger is a step filter. Okay, whose goal will be to filter all the steps that are useless when debugging Scala code. This is the interface of step filter, and those are the methods that we want to skip. So we want to skip the mixing forwarders, as we saw, but maybe also we want to skip the getters and the setters, because those in Scala, they just return the value of some field, or they just set the value of some field. We also want to filters the bridges, which I don't have time to explain, but those are also low level detail of implementation. And then maybe we also want to skip all the synthetic methods, so methods that are generated by the compiler in the case class or case objects. Okay, to implement that, I will use tastyquery. Tastyquery is a new library created by the Scala Center, and it's a very good library. It can read tasty files in Scala 3 jars, and read them into tasty trees, and it makes them available with a very good interface. It can also read Scala 213 signatures and Java signatures. So what's good with tastyquery is that it can read everything that you want to know about some compiled Scala program. Also, it can erase the signatures, so the Scala signatures, into Java ones, and that's useful when you want to compare some class files with some Scala code. Okay, and this is the implementation of the should skip step method, but I don't have time to go in detail. So we try to find like the symbol in the tasty file of a Scala method, and if it's a synthetic one or if it's an accessor but not a lazy accessor, then we skip it. Okay, and that's the new version of the scala-debug-adapter with the step filter. It's version 3.0.0. It's not yet available on methods. It will be soon, maybe in a few weeks. And that's it. That is for the debug adapter. A few little known debug features that are really cool and that you should try are the hit count that we saw, the log point. So the idea of a log point is you put a breakpoint that will print something to the debug console. So the program won't stop at the breakpoint, but it will print something. So this is the alternative version of adding a lot of printlns in your code. A data breakpoint is for the program to stop when some variable is accessed. This is very useful, I think, and it already works. Restart frame, we saw it. Edit value. So in the in the variables, like you can change the value of a variable. So if it's a local variable or if it's a field of something that can access in the local variable, you can change the value at runtime. Run to cursor. Okay, so this is, you go to some places. So of course you need to start the debugger first. Debug. Okay. Get all nodes. Okay, there is a condition. Okay, remove it. Okay, now I want to go directly into maybe get all nodes. It's here, maybe in read all bytes, like here. So I can right click and say run to cursor, and it just ran until this point. That's useful if you don't want to add a lot of breakpoints everywhere. You can do that. Okay, that was about the little known debug features, and then is what's next? Even more Scala friendliness. So there are even more things that we can improve to make the Scala debugging experience better. And one thing we can improve is unbundling the variable names. So when a variable is captured by a method or class, it will have a mangled name like this, $1, and that's not the name that you can read in the source file. So it would be better if the debugger shows the source file name and not the class file name. Another thing is improving the call stack. So the Scala call stack is really complex sometimes. Here, I show that we have the mixing forwarder that we saw earlier. So this method is mixing forwarder. This is also one. And maybe we don't need to show them, or maybe we should show them with some better names. Also, the types are erased, and maybe we could show the real types, the real Scala types. And that's we can do using tastyquery, because now in tastyquery, we can read the real Scala signature and show exactly what the signature is. One last thing we can do. Okay, so when I want to evaluate an expression, I put a breakpoint on a line. But sometimes in a single line, you have several scopes. So here I have the scope of the list, which is maybe a method, but I have also the scope of this lambda. And if I want to evaluate x, the compiler expression, the expression compiler needs to know that I want to evaluate x in this scope and not this scope. So maybe we could use the information of the column of a breakpoint to evaluate an expression properly. And the last thing that would be very, very good to do is to review all the debug line tables generated by the Scala3 compiler. So most of the time they are really good, but sometimes the Scala3 compiler generates some really weird debug line, and it's really hard to understand where you are at the program on those debug lines. Last thing we need is U. Okay, why do we need U? Because the stability of the debugger depends heavily on the test suite. So each time there is a new version of the compiler that is released, that new version could break some features of the expression evaluator. And to ensure that nothing breaks, we need to test a lot of different use cases. But to find those use cases, we need people to try the debugger and to report all the bugs. So that's how you can already use the new version of the debugger. So it's not available in Metals except if you add this plugin into SBT with the new version 3.0.0, and then if you use SBT as a build server. So already today, you can try this new version with the step filter and the expression evaluator and all. To switch to SBT as a build server, you open the command palette and you run switch build server. And that's it for me. This is a link of the debugger repository, and this is my name on Twitter.
Adrien, thank you so much for that wonderful presentation. It looks like we have a few questions. We're running out of time. We'll see how many we can get through. So let's jump into it. Do you have any further plans to make the debugging of concurrent programs easier?
So currently, no, I don't have plans. Also because I don't really know what people need to have a better concurrent programming debugging experience. And also, because we need to know also what VS Code can propose to improve this.
Okay. Next question. Are you planning any IntelliJ integration?
So that's a good question. So IntelliJ, they use their own debugger. We don't need to do anything. It works well. I mean, for debugging, like adding breakpoints and all. For expression evaluation, they have their own compiler mode that they parse basically the expressions themselves, and they use their own abstract syntax tree to then be able to evaluate these expressions. This works most of the time, but on some complex cases, it does not work. And in those cases, maybe they want to use the Scala3 expression evaluator. So that's something that we are thinking we can do to add the Scala3 expression evaluator into IntelliJ.
Excellent. All right. And our last question, is it possible to set an automatic debug configuration for this compiler?
I don't really understand the question. To set an automatic debug configuration for this compiler. So do you want to debug the compiler? Which compiler? The Scala3 compiler? Or or the expression compiler?
Maybe we can get some more clarification on that on Hopin, but we'll go ahead and wrap it up there. Thank you again for being here. What a wonderful presentation, and I hope you enjoy the rest of the conference.
Thank you, Jason.
Thank you.
Fire in retro rock.
Roger, Matt. Ready to eject.